In this video, we will talk about change of variables for double and triple integrals. There is a lot to cover, and it is all summarized in these first three slides. In the first slide, we will talk about coordinate transformations in general. In the second slide, we will talk about the Jacobian and how we use the Jacobian to do a change of variables for the double integral. And then we will do the same for the triple integral. We will define the Jacobian, and then we will do a change of variables for the triple integral. We will start by talking about coordinate transformations. We'll let t represent our transformation, and we'll start with R2 to R2, and it's a map of class C1, so we do have derivatives that transforms the UV plane into the XY plane. And we are interested in how certain subsets D star of the UV plane are distorted under T into subsets D of the XY plane. Our first example is T of UV is equal to U plus 1, B plus 2. In other words, the X coordinate is equal to U plus 1. The Y coordinate will equal to B plus 2. So you can think of this transformation as shifting everything over to the right by 1 because the x is shifted by 1, and shifting everything up by 2 units because y, you're basically adding 2 to the y direction. So in particular, if we look at the point 0, 0, we're going to have, it's going to map to the point 1, 2, which is this point 1, 2 here. If we look at the point 1, 1, it will map to the point 2, 3, which is here. And essentially, again, everything in this kind of square domain between, or the unit square between 0, 1 and 0, 1 is going to be shifted over to the right by 1 unit. So this whole square shifted over to the right and then raised up 2 units. Our next example is S of UV is equal to 2u and 3v. And if you recall, when you multiply by a scalar, you just scale the vector, or you increase the vector length by 2 in this case. So the vector 0, 1, or the line 0, 1 is going to be stretched out to 0, 2. Similarly, here, our vertical vector here, that's unit length 1, is going to be stretched out by a factor of 3. Or you can also think of this as the point 1, 1 is now going to map to the point 2, 3. So again, everything is essentially the same, except that all the points are kind of spread out by a factor of 2 in the x direction and spread out by a factor of 3 in the y direction. Now you can do this function composition. You can both shift your unit rectangle or your domain, and then you can stretch it. So here we have t of SUV, so that would be t and s stretches by a factor of 2 in the x direction and 3 in the y direction, and then you apply t. So you shift it over 1 unit to the right and 2 units up. And so this is what our composition looks like. We have our unit square has been shifted over 1 unit to the right, 2 units up, and then stretched out by a factor of 2 in the x direction and 3 in the y direction. This next transformation, number 4, is a little less obvious to see what it does because each component involves both variables u and v. But if we want, for example, to see what happens to the unit square, we can just look at piece by piece, edge by edge. So for example, the bottom edge over here that I have in red, that's when v is equal to 0 and u goes between 0 and 1. So for this bottom edge, our transformation of u0 is equal to, where's t, is u plus v, which is 0, so we get u, and u minus v, and v is 0, so we get u. So here we have this line here, which is the bottom edge, is going to map to the line u is equal to v. So I have this red line here, which again is what this bottom edge maps to. Then the top edge, and also u is going from 0 to 1. The top edge here, where u goes from 0 to 1, and v is equal to 1 over here in green. I can plug this into my transformation. So if I have u1 into the transformation, I get u plus 1, and I get u minus 1. So you might see the relationship here right away, that v, this term here, is equal to u minus 2. But I probably shouldn't have used u's and v's here. I should have used x and y's, because really we're transforming to x and y. So taking another look at this, if x is equal to u plus 1 and y is equal to u minus 1, then the relationship between x and y, so y is equal to u, which I substituted x minus 1 here from this equation, and then minus 1. So y is equal to x minus 2. So this green line then gets mapped to the line x, so I come down 2 units, and then I have the slope of 1. I have this line here, which is parallel to this line, the red line. Continuing on to the left edge, and that will be where u is equal to 0, and v goes from 0 to 1. Then I can plug in the 0v into my transformation, and I'm going to get v is equal to negative v. In other words, I get the line x is equal to negative y, or u is equal to negative v. So that is this line here, x is equal to negative y, the blue line. So this blue edge gets mapped to this line, and then finally you can see the right edge, which is where x is equal to 1 and y is equal to v. When you plug it into the transformation, you get v plus 1, y minus v. So looking at this, our x is equal to v plus 1, our y is equal to 1 minus v. So plugging in x, or v, is equal to x minus 1 from this equation into this equation here, we get that y is equal to minus x plus 2. And so that's this line here. We have y starting at 2, and then it goes down with a slope of 1, negative 1. So it's parallel to the blue line. This could have been done even easier because this is a linear transformation, and linear transformations can be represented by matrices. And what do I mean by a linear transformation? It means each of your variables u and v can be multiplied by a scalar, a and b, and then they can be added together. So here you have, for the first term, you get u times a plus b, v times b, and then for your next term, again, you can multiply each variable by a scalar and then add them together. And then this can be represented by a two-dimensional matrix here, and you multiply by your uv to get a times u plus b times v for your first coordinate, and your second coordinate is going to be cu plus dv. And for our example, we'll use our previous example here. T of uv is equal to u plus v, u minus v, and we can represent that with this matrix 1, 1, 1, negative 1, and you can see that that would be u plus v, and then u minus v. And again, it maps our unit square into this square here, and in particular, if it is a linear transformation, then it will take parallelograms to parallelograms and vertices of parallelograms to vertices. So also, if d star is a parallelogram in the uv plane that is mapped onto the parallelogram, then the area of d is equal to the determinant of a times area of d star. But more importantly, this transformation here, we kind of did a little bit of work to figure out what happened to the unit square. But actually, all we had to do was map the vertices, because it's a linear transformation, so it'll take vertices to vertices. So I can see that 0, 0 gets mapped to 0, 0. I can see that 0, 1 gets mapped to, so this is, where's 0, 1? 0, 1 gets mapped to 1, negative 1, which is over here. And then 1, 0 gets mapped to 1, 1, and 1, 1 gets mapped to 2, 0. And then I have my 4 points, and I can just connect them together because I know that parallelograms get mapped to parallelograms. So when possible, when you do a change of variables, if you can, linear transformations are especially nice. And that point is important enough to repeat again. So linear transformations are especially nice because they'll take parallelograms to parallelograms and vertices of parallelograms to vertices. And last, I should point out, not all transformations are linear. So for example, our transformation into polar coordinates is not a linear transformation. In particular, it's not even one-to-one. So for example, t of any radius r of 0, theta, gets mapped into 0, 0. So all real numbers of theta get mapped to 0, 0. And vertical lines in the r theta plane, given by r equals a, where a is a constant, are mapped to a cosine theta, a sine theta, and etc. So basically, it's not one-to-one, and lines get mapped to arcs and circles, and so it is not a linear transformation, but very useful. Our next topic is the Jacobian of a transformation. The Jacobian is a measure of how a transformation distorts the region of the area, and in particular, here's the formula for the Jacobian. It is the absolute value of the determinant of the derivative matrix. So you take the derivative matrix, which looks like each row looks like a gradient. So here's the gradient of x, gradient of y. If you are in 3 dimensions, gradient of z. You take the determinant and then the absolute value. Our first example of the Jacobian is for the polar coordinate system. So if we take, we first work with x equals r cosine theta. We take the derivative with respect to r, then the derivative with respect to theta, and then we do the same thing for y, our next coordinate. So dx dr is equal to cosine theta, and dx d theta is equal to negative r sine theta. dy dr is equal to sine theta, and then dy d theta is equal to r cosine theta. So when we take the determinant, we get r times cosine squared minus negative r times sine squared, and we will be left with r. In most vector classes, you'll do so many polar coordinate transformations that you'll remember that the Jacobian is equal to r, not that it's difficult to calculate. We use this Jacobian in our change of variables theorem for double integrals. So what this change of variables theorem tells us, if we have an integral over the region D, which is in the xy plane, we can map that over to the UV plane, and then D gets mapped over into D star in the UV plane, and then F, we have to map that over into the UV plane as well by our transformation, and then multiply by the Jacobian. Before we look at these two notes here, we're going to look at an example. So it says, let the elementary region D in the xy plane be bound by the graph of the polar equation r is equal to f of theta. So here we have r is equal to f of theta, and theta is going to be between theta 0 and theta 1. In other words, between this angle and this angle. So this is the region here that I'll shade in blue. We can do our integration in this space here, but we can also transform it into this space, which maybe looks a little easier, but in any case it's different. So theta is going to be between theta 0 and theta 1, and then we still have r as a function of theta. So if we want to figure out the area, calculate the area of D, this blue section here, we can integrate over D, dx dy, or we can make this transformation into polar coordinates. So we would have to, when we make that transformation, we do have to multiply by the Jacobian. And here is our integral. So we go from theta is equal to theta 0 to theta 1, and then r goes from 0 up to the function f of theta. And here's the Jacobian r, and then we're integrating the function 1, dr d theta. And then you can see it's worked out here. We will have more examples of polar coordinate transformations where the thetas are actually angles as opposed to just thetas. Anyway, the other couple of notes I wanted to say is one, that the change of variables theorem is valid for polar coordinates, even though it is not a linear mapping, and in particular, even though it, here we say that we want the function t, the transformation t, to be 1-to-1, and obviously the polar coordinate transformation is not, because it maps everything with 0 radius to a single point, 0, 0. But this theorem does work for polar coordinates, and the reason why it works is the set of points where t is not 1-to-1 is on an edge of D, which is the graph of a smooth curve, and therefore, for the purpose of integration, can be neglected. A second note is another way of looking at the change of variables in the Jacobian, and given a perhaps more complicated definite integral, we can make the substitution x is equal to x of u, where x is of class C1, then dx is equal to x prime of u du. So if x a, our endpoint is equal to x of a, and b, the other endpoint is equal to x of b, and x prime of u is not 0, then we would transform this a to b f of x dx is equal to a to little b, which we have here, f of, and we compose x of u, and then the x prime of u. So the idea is this x prime of u is sort of captured by our Jacobian. So you can think, and then finally, we can define our Jacobian for triple integrals, which again is just the determinant of the derivative matrix, derivative of basically the gradient of x, the gradient of y, and the gradient of z. And then for your change of variables, you need to multiply your integral by your Jacobian. The Jacobian for cylindrical coordinates is r. The Jacobian for spherical coordinates is negative rho squared sine of phi. So here is our example. So suppose we want to integrate this function e to the x squared plus y squared plus z squared raised to the 3/2, where d is the unit ball. So we're going to integrate this over the unit ball. So this cannot be easily integrated without a change of variables. And because we're talking about a unit ball, we'll use spherical coordinates, which I have written out here. So for the sphere, rho is going to go between 0 and 1, theta between 0 and 2 pi, and phi between 0 and pi. So we're ready to set up our limits of integration. And so for, but first I plug in my Jacobian. And now we're ready to set up limits of integration. So again, theta goes between 0 and 2 pi, phi between 0 and pi, and rho between 0 and 1. And then the rest is just integrating. It's pretty straightforward and plugging in. And again, this follows that same form I had talked about before in the triple integral video I did, in that the outside integral must have numbers. And then this one can depend on at most one variable, and it'll be this last variable here, rho. But it's okay if it has numbers, as well as inside here, this should depend on, at most, these two variables, the two outside variables, but it's okay if it depends on only one, and it's okay if it has numbers as well. Before we go on to do some additional examples, I'm just going to review really quickly the main points we've talked about so far. We talked about coordinate transformations in general. We talked about how we could compose them. We talked about linear transformations, that they could be represented by matrices, and those matrices are transformations that are one-to-one and onto, and they will take parallelograms to parallelograms and the vertices of parallelograms to vertices of the new parallelograms. And that's what made linear transformations really nice. So if you can choose a transformation that's linear, that's super. We also define the Jacobian for double and triple integrals as the determinant of the derivative matrix. For polar coordinates, the Jacobian is equal to r. For cylindrical coordinates, the Jacobian is equal to r, and for spherical, it's equal to rho squared sine phi. And then last, we use the Jacobian into our change of variables formulas, both for double and triple integrals. And now we are ready for some more examples. I did put the change of variables formula up here for your reference. And the first problem is to find the double integral of cosine x plus 2y sine of x minus y dx dy over the triangle bound by y equals 0, y equals x, and x equals 2y plus 8. Here I graphed out my triangle and I also calculated where the y equals x and the x equal plus 2y equals 8 intersect, which is at x and y equal to 8 over 3. To do this problem, I am going to try a change of variables. U is equal to x plus 2y and v equals x minus y. And how did I choose this as a change of variables? I looked at the arguments for cosine and sine. And that's what inspired this change of variables. And the other thing that's important to note is this, because this is linear, it just involves taking x and y, multiplying by scalars, and then adding them together, or in this case, adding plus negative 1 times y, then it has the added bonus that then this will be an easy transformation to make. Because this is a linear transformation, if I want to know how this gets mapped over here, I can just check my endpoints. So t of 0, 0 gives me 0, 0. T of 8, 0 is going to give me 8, 8. And t of 8 thirds, 8 thirds is going to give me 8, 0. So I plot my points, and this is my new domain, this triangle here. So next I need my Jacobian. Here, my derivative of xy with respect to uv. Unfortunately, my variable transformation doesn't have x written in terms of y, and I can do the algebra to figure that out, but I'm going to do something even simpler, which is this dx y over duv is equal to 1 over duv dxy. Here's my duv dxy. So I have the derivative of u with respect to x, which was 1, with respect to y is 2. Derivative of v with respect to x is 1, with respect to y is negative 1. So the determinant, I have my negative 1 minus 2, which is negative 3, which means my dxy over duv is equal to negative 1/3. Starting to set up my integral, so I have my Jacobian. I just went ahead and pulled it out in front, and it needs a negative. And then I have my limits of integration. I'm going to have x run from 0 to 8. I'm sorry, actually that's u is going to run from 0 to 8. And then my v then runs from 0 up to this line here, which is just, since we're going from 0, 0 to 8, 8, it's just u is equal to v. So v is going to run from 0 up to the line u is equal to v, so that to the value of u. My limits of integration are now set, so now I need to compose my function f of x of uv. So I first need to find my f of x over here, and then I just plug in my uv. So I have this integral here. And the rest is just integrating and evaluating. The only thing interesting or slight interest I have is using the half angle formula. The next example problem is to set up the triple integral to calculate the volume of a cone bound by az is equal to h square root of x squared plus y squared. So that's this cone here. And the plane z equals h, so there is a top to that. If I do this in rectangular coordinates, it seems very natural to me that x goes from 0 to a, and y is related to x by a circle, and then z goes from the edge of the cone up to the height h. But you can see when I integrate with respect to z, and then I plug this limit of integration in, it's going to give me something difficult, if not impossible, to evaluate or to integrate with respect to y. In a previous video in this video, which is about changing variables, the solution is going to be making a change of variables into cylindrical coordinates. So we have to have the Jacobian for cylindrical coordinates, which is r, also the Jacobian for polar coordinates. So now the integral becomes quite easy. Theta goes between 0 to 2 pi, r goes from 0 to a, z then goes, again, it's going from the edge of the cone to h. And the edge of the cone here is h over a, and then this square root of x squared plus y squared is equal to r. So this is how we would set up this integral in polar coordinates, cylindrical coordinates. This next problem is to let P be the parallelogram bounded by y equals 2x, y equals 2x minus 2, y equals x, and y equals x plus 1. Then we want to evaluate this integral over the parallelogram by making a change of variables. X equals u minus v and y equals 2u minus v. And here I have drawn the parallelogram. To get my new domain under this transformation, I'm just going to see how the transformation affects my vertices. So I have t of 0, 0 plugged into u minus v to u minus v is going to give me 0, 0. My t of 2, 2 is going to give me the point 0, negative 2, which I have plotted here. My point 1, 2 is going to give me the point 0, 1, which I've plotted here, and my point 3, 4 will give me the point 1, negative 2, which I have plotted here. So I am now in this rectangle. And a quick comment, the reason why I could just worry about the vertices is because this transformation is linear, because the u and v, all we've done is scaled them, multiplied by scalars, and then added them together. So here the scalar is negative 1, and I added, the scalar is 2 and negative 1, and then I added them together. Next, I calculate my Jacobian. So I take the derivative of x with respect to u and then v. So with respect to u, it's 1. With respect to v is negative 1. And then next with y, with respect to u, it's 2. With respect to v, it's negative 1. The determinant is equal to 1. Here is my determinant. And then I plug in uv into my function, which is over here, x times y. So my x is equal to u minus v. My y is equal to 2u minus v. And then the rectangle, so u goes from 0 to 1, and then v goes from negative 2 to 0. And then the rest is just integrating and plugging in. This problem was quite complicated to visualize, so unless you have really good drawing skills or maybe some tools to help you visualize, it's difficult. So I am going to skip this one, but I have left it here for your reference. Now for review, I have 3 problems for you to try. So pause the video, give them a try, and on the next slide, I'll have solutions. Here are my solutions for the first 2 problems, and here's the solution for the last problem. And that is it for this video. Thank you for watching.